Good evening, and welcome to another presentation for Data 620 with Professor Alan Ladon at CUNY School of Professional Studies. My name is Sam, and this presentation represents the work of myself and David and Euclid, my group members. We have chosen a data set from Stanford Snap Sources, which is composed of roughly 500,000 reviews of foods from Amazon in their early days. We'll be building a two-mode network consisting of food product codes and customer codes from customers who reviewed the items. So we're trying to find out what are the most important food products from this data set, from this time period. And we're going to try and discover this by using basic network analysis skills that we learned from Social Network Analysis for Startups, an O'Reilly book published in 2011. So because this data set's really large and projecting bipartite graphs, doing some of these other methods takes a fairly long time. I've run all of the code blocks already, and we'll just go through the presentation without running it live. So sorry for that. I really enjoy a live presentation myself. I don't know, maybe that's ridiculous, but let's cut into it. So we start by importing some basic libraries: request, networkx, pandas, numpy, scipy's in there, regex, matplotlib, and dill, though we don't really need dill actually, because we've commented out the code that uses pickle objects. But okay, so I already told you about the data source. We've pre-processed this data in a couple of ways. It's so computing intensive to do regex across that many things that we saved the data in a CSV file and uploaded it to the GitHub where this code lives. And so if you'd like to check it out, you can just download the CSV file and run the code as is, and it will load all of that pre-processed data directly into your notebook, provided that the file is in the same folder. So let's get going. We open the file and read it in. Each record is separated by two new line characters, \n/n. In each record, the first line contains a product ID, and the second line contains a customer ID. So we can extract some information based on these findings. We separate the whole data into individual records. Next, we separate the lines within each record. By using a regular expression, it is possible to extract a product ID from the first line and a customer ID from the second line. Then we append the product ID and customer ID to a data frame. Process takes a while. Maybe don't do it on your own computer. After that, we can load the CSV file directly. So this commented out code over here is the way that we did it the first time. But now, we just use the pandas built-in read CSV function, which is really fast, all things considered. And it looks like this. We have row numbers on the left going up to 568,000. So there's almost 600,000 of them, actually. Product, key, and a customer ID. I think the actual product names and the customer screen name, their little handle on Amazon, are available in the dataset too, but it's not really necessary for what we're doing. So we're just using these two things. Before using the data, we can remove some duplicate records. Same customers sometimes leave more than one review for the same product, and that would skew some of our figures. That would offset the things that we're trying to figure out about these products. So we remove them with simple drop duplicates function. Then we create a graph. We start with an empty one, and we load in the nodes and edges that we have. So then you can check the number of nodes, the number of edges to make sure that everything is going right. This doesn't tell you directly if everything is done properly, but if the numbers are exactly the same, the likelihood is very high that everything went according to plan. So that's a good enough test for us. Now for the analysis. To analyze the network among the customers, we project the graph onto the customer nodes with the weight of the edges equal to the number of common products purchased by connected customers. So if people are buying and reviewing all the same items, their connections, we see them as more important because we're trying to identify subgraphs or clusters within this data that show products that were bought together, or maybe things that cause people to want to buy more things from Amazon, more similar things. Perhaps they're reading each other's reviews. Maybe they're not. I don't know. I review lots of stuff on Google, and I do find myself reading other people's reviews. So maybe that's what's happening. We make a bipartite graph. So if two people are connected by the same product, or I guess in this case, if two products are connected by one common reviewer, then we find that the two legs form one connection. So yeah, that exploded our graph quite a bit to the point where we have about 11.5 million edges. Quite a lot. So yeah, again, not running this live because that takes a long time for my computer to deal with. So we can check the length of connected components here using the familiar set theory format that's very common in Python. We like doing things Pythonically. So here we have 15,550 isolated nodes and some other components with at most 126 nodes. Surprisingly, there's one component which just has a lot of connected nodes. It seems like most people do have common demand of products in this case. But we still don't know how strong the connection is. Dataset is a bit too large for our purposes, and we can make it a bit more manageable and more telling by employing the island method that we have used before. That is simply trimming the edges with less important weights to reveal only the heaviest connections. And you'll find subgraphs, I guess, after trimming the edges, which show you the most important information that should have a great impact on your business if you use it properly. So here is a method to trim the edges with a default weight of 1, and another method which calls that with default iterations of 5, and then we call the function. After checking the results, the threshold number of nodes of the resulting subsets, number of nodes in the connected components, and the resulting subsets and the associated frequency. So here is a little printout of what that looks like. So for thresholds 1 and 10, we can see a large connected component in the subset. The subset with threshold 10 is about 3,000 nodes, which is a good one to be used for our analysis. So we'll focus on that. Let's look, I can show it again. Okay, so yeah, threshold number 1, threshold number 10, 53,000 is like maybe too much. We could do it, but yes, we like this subset here. So here's some basic important statistics from the subset. You can see the degree, centrality, eigenvector, closeness, and betweenness for all of these things, and we can summarize it and show the general deviation for these figures. We can see the average degree and average closeness are significant. They're useful. eigenvector is pretty small, betweenness is pretty small. So maybe we can't see obvious things there. The nodes in the subset are strongly and closely connected. Since these are isolated islands, the betweenness is predictably small because there's no connection between the islands. We can confirm our findings by drawing a picture. Following is a figure of these islands. There are a few small ones around a large condensed island in the middle. So the next graph is the largest connected component of the subset. It's a cluster in the very center that you can see up here. You can see that the nodes are really close and well connected. The customers in the center are the most valuable for our question because the group is pretty large. It definitely outweighs all the other little specks around the graph. And these people buy many of the same things. So there's maybe by doing other studies we could find more out. Maybe there's even more interesting information in subset number 1, which we didn't choose. So now we know which customers are very valuable, but what about the products, right? What are the products, and maybe why are people buying them together frequently? I don't know if we can find that out from this information, but to analyze the network among the products, we do exactly the same thing we did with the customers, but in reverse. So we project the graph onto the product nodes this time with the weight of the edges equal to the number of common customers purchasing the connected products. So there's about 75,000 connected products here, and the total number of connections is, what is that? It's 1.7 million. That's a large number. So again, we can check the length of the connected components. Similar to the customer network, the product network has a large component with around 50,000 nodes and other components with few number of nodes. So the result is showing that most of the products are related to each other in some way. And we can find out how closely they're related by using the island method again. We trim away the things that don't matter as much, and we're left hopefully with some telling information about the most important things. Again, so here's some basic statistics on that. We select the subset with threshold number 122. This one right here, the second one. It's got 472 nodes. In this subset, the lengths of the components do not have extremely large difference. This is reasonable because you can have 1 million customers connected together by purchasing the same product, but you cannot have 1 million products purchased by the same customer. So just a little idiot check there, I guess. Common sense check, maybe is a better term. We can create a summary of the nodes and look at their basic statistics the same way that we did before and check the summaries. The average degree is high, however, closeness is low for the product network. This implies that these products are popular and bought frequently by some common customers. However, there are very few bundles of products that these customers bought frequently. So we can draw some more things to try and confirm what we think we understand. We've got a hairball, but there's no closely connected large subgraph. So we can examine the graph of the most connected components, and it looks like this. Still a bit hairballish, but there are definitely some products that are kind of the most important. Maybe they require some of the things on the outside, or maybe they're required to go with some of the other food items. Perhaps they're staples, like a special type of noodle or something that you might want to buy to make a bunch of different other dishes. Since this is only food products, you can see the nodes are well connected, but they're not very close. So though these products are not close, we know that they're the most popular products bought by most of the customers in the data set. So how do you use this information? We have limited inventory, and to get around logistical problems, which Amazon is really good at, we focus on pushing these things the most and try and buy them and sell them in the biggest bulk that we can. So hopefully that makes some sense to you, lovely viewer. And that concludes the presentation. So thank you for listening, and have a nice night.